Welcome back. This is the fourth lecture in the Toolbox Basics course, and in this lecture I'll be describing interpolation. Now remember from the previous lecture that I described how contemporary ODE solvers such as ODE 45 use variable step algorithms to integrate a solution forward in time. Now that variable step representation of the data is fine for plotting, but if you want to perform any sort of serious analysis of that signal, then you need to transform it from variable time steps into fixed time steps. And that is what the interpolator does. So if you were to run this manually in MATLAB, then you would use the interp1 function. But the Toolbox GUI does this step automatically with its built-in interpolator. And that interpolator runs every time the solver returns a new solution. So now I'll show you how we use that interpolator in the graphical user interface. So here is our old friend, the linear ODE, and here is the time series of the solution computed by the ODE 45 solver in this case. And we can double check the time steps taken by that solver, and we can see the time step varies as the solution progresses. And returning to the time portrait, we can highlight those time points like we did in the last lecture. And if I want to see the interpolated version of this signal, I can turn off this auto steps option. If I turn auto steps off, then I'll be looking at the interpolated version of that solution. So I haven't changed the solution. The time steps used to compute the solution are the same. The solution itself is unchanged. It's just that I am now interpolating it with a coarser time step. And in this case, the time step is 1 time unit, and that corresponds to this value here. Now you might remember from last lecture I described how that step parameter can be used to change the step size of the fixed step Euler method, and that is true, but when the solver is a variable step method such as with ODE 45 or pretty much any other solver, then this step size is used to control the interpolation time step. So if we change this to 0.5, for example, we will see this exact same solution, but now reinterpolated at the smaller time steps of 0.5 units. Let's drop it down to 0.1, and you'll get the idea. 0.01, and we're getting finer and finer interpolations of the exactly the same solution. Okay, the solution is not changing. The solution is not being recomputed. It's just being resampled. Now, if we look at the solver bar down at the bottom of the user interface, we can see the time taken by the solver. Well, of course, that's not changing because the solver is not running, but the time taken by the interpolator does increase as we go for finer and finer time steps. It also consumes more memory. So be careful not to use too small of a time step, otherwise you might find the system locks up. And has it locked up for me here? I'm not sure. Is it responding? Let's put it back to 0.1 just to see. We're okay. Everything's fine. All right. So that's the interpolator. So keep an eye on the interpolator. Make sure the interpolator is not using you don't want the interpolator using more CPU time than the solver, for example. So just be mindful of that when you're plotting things, to keep the step size or keep an eye on the step size and that interpolator time. And I'll just wrap up by showing the same thing in the phase portrait. It depends on each panel whether you're showing the auto steps or the fixed steps. Here I've switched to fixed steps. I better turn the time points on. There's the fixed steps. Now I'll turn auto steps on. There are the auto steps. Back to the interpolated fixed steps, and let's make those fixed steps even smaller, 0.01. There we go. Now you see the fine interpolated signal. Not all panels support variable steps. For example, the Hilbert Phase panel, which computes the analytical phase of a signal. Sorry, that's the wrong panel. Let's close that panel. The Hilbert Phase panel computes the analytical phase of a time series, and here it plots that analytical phase on the unit circle as a cylinder in time. Now that particular panel, like several other panels, does not have the auto step option because it only supports fixed time steps, and you can see that the time axis here is using fixed time steps. Okay, so here the time portrait here, the time axis shows the size of the time step. If I switch back to auto steps, you can see that time label switches to dt equals auto. Anyhow, that's the interpolator. It's not that complicated, but it is something you have to be mindful of. Otherwise, you can be quite confused by the plotting results sometimes. Okay, so that's the end of this lecture, and I promise that will be the end of using the linear ODE. We'll get onto a neural model in the next lecture.